Hi, everybody. My name is Theodore. I'm the president of Illinois Robotics Space. Me and everyone else on the team here so happy to be here with you all today to learn about robotics, a little bit about what NASA and the Artemis mission is. So, does anyone know what NASA is, and also specifically what it stands for? You hear NASA, what does it stand for? Awesome. That is very correct. So NASA, they they do a lot of development for space related applications, but I think one thing that you all might know is that a lot of the work that they've done over the years also turns into real technology that we use at the end of the day in our daily lives. So for instance, computer chips, that is one great area of engineering that was not fully developed at NASA, but was definitely helped to get accelerated into the laptops and devices that we have today. On the other hand, today we'll talk about some of the more, in my opinion, this is my favorite topic, robotics. What is a robot? Does anyone know? Could somebody let me know what that is? Yes.
Robotics. Robots are
I would like to kind of showcase the fact that they're very much not just one part of the system, but typically, like, I'm a computer engineering student. I program computers and I learn about how they work. But at the end of the day, a robot is a physical system that works in the real world. And so, to build a robot, you have to understand many different disciplines, from the mechanics behind it to electronics and all the way to programming that you'll eventually do on it. So without further ado, I'll quickly again introduce myself. My name is Theodore, and I'm a computer engineering student, junior right now. I plan to graduate in about a year from now, and I have a couple of hobbies that I think are fun: skiing, mountain hiking, and I like cooking. So just to check, can everyone in the back hear me clearly? Exactly. Okay, good. So we're gonna first talk about a little about why space. I think it's kind of awesome the fact that, like, if you've ever seen pictures of Earth from space, it's just very breathtaking. And at the end of the day, going to space is more of like a challenge for the advancement of humanity. And I consider the task of going to space to be extremely challenging because on one hand, you get to experience and see what the world outside of Earth looks like. But on the other hand, it is immensely difficult to put people like thousands of miles up into the sky away from Earth and then have them return safely. So that's what NASA engineers were doing a good number of decades ago when they were doing the Apollo missions. And since then, we're now back to having our interest in continuing this space program. But you might be wondering why. Like, I don't know, you all are middle schoolers. There's gonna be a lot of times that you'll have a chance to see whether or not the space engineering will get to the level where you all could like go up into space. If you've all seen videos of Blue Horizon, or yeah, Blue Origin, like they send people in these like rocket ships up to like the outer atmosphere of the Earth, and then you can like float in like zero gravity and look around and then come back down. So I recommend you look that up if you don't know what that is. But one thing to note is that this task of doing space exploration produces so much like benefit to everyone else in America and the rest of the world. So not only do we advance tips, but we also advance our understanding of chemicals, manufacturing techniques, etc. So everything here in this room could probably be in some way related to the development of the space program that has happened in previous years. So just because it's not immediately like a product that you can go and buy, you can't buy a rocket ship and immediately, it doesn't mean that there isn't a huge benefit to everyone else in the country. And then here you can kind of see some of the famous electronics that kind of came as a result of work that was done by NASA. But on another like sort of science end, I guess it's kind of cool to figure out like what's out there, like what exactly is on the moon. I think you might have heard about the spaceships from India that went to the southern pole, I believe, of the moon. So in that case, like, how do they want to go there? Like, it's like, okay, we just send a rocket there, but they wanted to see what was there and they found water. And that's a great, thing to learn about the moon because it looks dry, but really there's actually water in there. So maybe you could drink that, or if they're thinking that in the future, you could use that as a fuel for like setting up a station on the moon, leave Earth and go to Mars. So, in general, sort of, I would just space exploration just opens up the ability for you to just discover and explore whatever you're curious about. And well, I think these pictures are pretty cool because you don't really see that on Earth. Like a bunch of stars or the big red, planet, the Mars. But last time that humans went to the moon was back in the 70s. And you can see here in this picture, we have the Apollo mission. So they had multiple missions where they were sending people up to test going to the moon, testing out different systems. And actually, this is a super important part of engineering. You want to make sure that everything works exactly the way that you expect it to work. You don't want any engineering failures to occur. And super smart engineers will always make sure that there are backups, especially the backup systems, especially if there are going to be people on the rocket. And so what 50 years since then, NASA is planning to do an Artemis mission. That's what they've called it, and they've already done the first two Artemis missions, 1 and 2. And what they've done is they've basically shown that they can take a rocket and send it up into orbit around Earth and then come back. There weren't people on that rocket, but it was an extremely important demonstration of just how safe technology could be for sending people to the moon. Because hey, if they did it in the 70s, the expectation is that we want to do better than that. And we'll be learning alongside from the challenges that happened in the 70s, but also from the new technologies that we're working to integrate to get us to the moon. Also, if anyone has questions while I'm talking about these topics, feel free to raise your hand. I'll call you. But one thing that you also look out for is the manned launch date that they have postponed. It was going to be in 2024, but you all will have to wait until September 2025. And on that mission, they will have 3 astronauts who have been chosen. Those are 4 who have been chosen, and those 4 astronauts will be going up into space, going around to the moon, not landing, but coming back. And as a result, we'll get to see humans going to the moon once again, which, hey, it's been 50 years. I would love to see that too. And here you can see this picture of what current rocket design looks like. I'm not an aerospace engineer myself, but that looks pretty cool. It's huge. I think like this room that we're in right now is already like pretty big. And that rocket would just barely fit in this room. So if you're thinking about the scale of it, just the circumference of it's just the diameter of the rocket is already absolutely ginormous. But I want to show you what NASA thinks about how they're going to go to the moon real quick.
Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will the Artemis mission look like? Everything is designed and tested with the most important element in mind, the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system with engines capable of the crew module to safety during launch and takeoff. To accomplish the task of launching a crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive lower stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there was no stopping in the concept. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent on boost. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignites the exploration upper stage engines to leave Earth in time. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intercept the moon days later. Once this burn is complete, the upper stage of SLS is jettisoned, and the crew aboard Orion coasts for several days toward all that awaits them. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as expendable lunar command control or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach, free state. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at the station, on pre-stage a robust internet and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal one between Earth and all that lies behind. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transferred to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built with 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbit of Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit, and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released. The crew module is oriented at heat shield first. Entering Earth's atmosphere, 25,000 miles per hour, the friction of air slows the line considerably. were also subjected to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes need to be tested and produced for this moment of deploy, accelerating the climb to just 20 miles per hour for flight. With each successful mission, Artemis ushers in the next wave of men and women to explore on their own and prove that together we're ready to go.
No, I think it's okay how they are. I think it's easier to see. Okay, so what were some things that you all saw in video that oh, were interesting? Sorry. Currently, I don't believe it's orbiting, but that's the plan is to have is to then have like another module that will be orbiting the moon gateway, as they call it, and that module actually it serves the purpose of mainly communication. Because what I thought was interesting is that if you're on the other side of the moon, you can actually send a radio signal through the moon to the Earth. So for that little bit of time that you're there, you won't be the astronauts won't be able to talk to Earth, which is actually a couple of hours, I believe. Cool. What else did you all see? The I think those characters like I I I enjoy to see we have a rocketry team, and it's so much fun watching them test out their parachute. What they do is they pick them up, and then they have these sensors, and then they run around with the parachutes behind them to test how effective they are producing drag and like or resistant parachute. Cool. What else? Yeah, can you say that? Yeah, I think some of the parts are meant to their goal there is to be reusable. Definitely the like the capsule would be absolutely amazing. Uh, yeah. How do they plan? This is actually very interesting. When you go into space, you don't have, there's no like wind or like there's no like yeah, there's basically like no wind. So like here on Earth, like it's very unpredictable for like an airplane when it's flying from place to place with its planet. But in space, because there's no air resistance as well, you can exactly where it will land without, from the second that it leaves the Earth's orbit, because only gravity will be acting on it, and at that moment when only gravity is acting, there are very simple math equations that you can use to precisely calculate. Okay, it's going to go around like this. It's going to get to the moon. It's going to reach the. It's going to get pulled by the gravity of the moon, and then it's going to get pulled back to Earth. And you can figure out, oh, it's going to land in the Pacific or the Indian Ocean, something like that. And they pre-plan that very precisely, but it is very much a timing concern, and that's why and that's another part of like why they have to sometimes delay the launches, so they can make sure that the path that the rocket takes is correct. Because even though in our like actually models of the solar system, it looks like the moon is on a perfect circle. It's not always like that. Its orbit isn't precisely like that, and that means that there are some cases in which if you launch a rocket on on a certain month, it will take longer to get to the moon than if you launch it on a different. Cool. We'll move on to talking about how exactly Robotics role plays into this. So I think you all saw that when the astronauts get to the moon, they don't want it to be just a barrier. They want there to be research there. They want there to be supplies. They want there to be stations available for them to do things. And it would be very dangerous if the astronauts had to go on the moon and then manually do all the labor to move things around. So instead, that's where robotics comes in. And that's where Robotics, the competition that we compete in every year, where we go down to the Kennedy Space Center, that's where we all come in. NASA wants to build, wants to have robots automatically go through and autonomously manipulate the surface of the moon in order to build things. And I'll show you some pictures of some of the things to have in mind a little bit. But in general, NASA takes a look at these competitions to get ideas from. So whatever we do, they'll take a look at it. Their engineers will be like, okay, maybe we could consider doing that on the real rover. So although our rover doesn't physically go to the moon, it does in spirit. And here you can see a little picture of what the arena that we eat in looks like. It's a simulated lunar environment. It's not actually, lower gravity or, there is air, but you can see the little dude in the back with the suit on, because the lunar dust, it's not like sand exactly, which is kind of interesting. Very fine. It's more like, it's way more dusty actually than sand would be considered. And so you have to wear this respiratory protective suit in order to filter the air. Otherwise the dust can irritate your lungs. On the other hand, you can see here there's a robot, and our arena looks like this. We basically have this space where the robot can drive around on. It's uneven terrain, and also the top layer is this lunar dust, and below it there's little rocks as well mixed in with the dust. So it's uneven. It's not like driving on a road. And what you'll see is that there are also craters and also these rocks that are obstacles there. But one thing that's interesting about this is that if you're driving the robot manually, well, in real life, you're not going to be able to be on the moon to drive it with a controller. So you'll have to look through the camera feed that the robot sends. And you'll actually, for this competition, we're in a different room than where the robot actually is. So that's quite interesting, in my opinion. Very challenging problem with your program. And then this year's competition, the job is to build a little mound of the material. So you have to drive from the bottom left corner to the top right and excavate the ground material, and then bring it over to the bottom right and deposit it and build up as much of a hill as possible. And the reason they do this is so that you can start building different buildings for different protection for buildings on the lunar surface. But here's a video of a robot running on the arena. So hopefully this will give you a little bit of a sense of what it does. You might notice that it's not really moving that fast, and that's because typically these strategies for having the driving the robot around, they're much slower. And so full autonomy is really what we're going for here. In this case, this is manually controlled. So there's a camera input, and then there's also the fact that there's some delay between the signal getting from the moon to the Earth. So that is also included here. But on the other hand, the robot, this design is trying its best to turn and go to the opposite end. This was, by the way, a previous competition. This year is the new one where we have to build this hill, but it still includes excavation. So here you can see this robot has a excavation mechanism, and it will spin and dig up the material underneath it, hold on to it, And then its job that year was to bring it back to where those people in the back are standing and deposit it into this like sieve. Yeah. But in general, I just want to iterate the importance of doing this type of doing engineering to solve some of the problems that are on that like come along with, or sorry, to I want to demonstrate like some of the benefits of actually solving a problem using engineering and putting the robot on the moon. The main like goal is that there's resources on the moon, and NASA would like to actually utilize those. And clearly, you already heard before, it's mainly so that it can be a station to get from the moon to Mars. You know, we have enough water on Earth, but it'd be great if it had it there. And so that's one of the things that they're interested in. Otherwise, here is a little render of sort of the expected construction that the robots will be required to do. So here are these semicircles with of hills, and there is where like the astronauts will want to land. So that's a lot of material to move. I'm not sure that if you were on the moon yourself, you'd want to do all the digging to move it around. And this is us. We're Illinois Robotics in Space, like I said before. But here's some of the things that we do. So we have five teams that we have on our that we have, and we do everything from scratch, all at U of I. And so here in the top left, you can see a last year's robot. We design all of that on our computers in a CAD software, which stands for Computer Aided Design, and it's all manually tested, and then we manufacture it by hand out of aluminum and different 3D printed parts. Here we have a PCB, which, if you're not familiar, it stands for printed circuit board. This is basically what is inside of all of your phones, electronics, etc. And it's what has all the wires and capacitors, etc. And in fact, I guess later on, when we're all in groups, I could bring this around for people to see. This is one of our previous PCBs. It distributes power to the rest of the system from a battery. And there's a big red button here for safety. So if the robot, catches fire or something, you come here and disconnect. Otherwise, some of the components that maybe you have or have not heard on, but I recommend that you take a look at are, here we have capacitors, here we have inductors, and then there are also resistors on here as well. So you can ask the people at the tables, in your groups, what exactly those are if you're interested. Then we also have our outreach team, which is us here today. And then we also have a systems team. I want to comment on the systems team because their job is not purely to do engineering work. Their work is more focused on making sure that everyone fulfills the requirements. Because typical day in Iris is mechanical team does some work on the robot, they pass it on to the electrical team. The electrical team does some more work, and they pass it on to the programming team. Well, we got to make sure that everything is going smoothly. Otherwise, the electrical team is going to see, oh, there's a problem with something the mechanical team did. They're going to send it back to the mechanical team. And then it's going to go forward and back like that at the time. And then it's never going to get to the programming team. So making sure that you have this sort of organized structure of breaking apart the work is exactly what the systems team is focused on. And they also make sure that, the system is safe. We need to have that red button. They're the ones who make sure that we have that red button. And then we have the autonomous team. This is my personal favorite. I study robotics, like autonomy, decision making, and planning. So in general, I study algorithms, or just you leave a robot to solve a problem, you should be able to do it by itself. And that's exactly what the autonomy team does. We write algorithms and systems, software systems that allow the robot to perceive its environment, see where the craters are, see where the
obstacles are, and then plan a path around them. Take that path, excavate material from the ground, put it back inside of its frame, and then drive it back and drop it off where it needs to be. So that's actually going to be kind of the main thing that you'll be exploring today. You'll have to see what it's like to, I like to think of it as, how do you think like a robot? Because for us, it's really easy to say like, oh, we want to go forward and stand on the black line over there. But at the end of the day, how does the robot, interpret that problem? How do you program it to do that? How do you get it to stop exactly at the black line instead of, 10 feet farther away? But apart from the activity that we're going to do today, I also want to comment on some things that you all should look forward to in the years to come for if you're interested in doing STEM related projects. So first off, if you have a Lego robotics team, you can join that. I used to do FIRST robotics when I was in high school, and I did Rex robotics while in middle school. So I found that those were extremely interesting challenges for me to work on developing my engineering skills. And also at the end of the day, you get to make a little robot that moves around and like drives around, and that's so much fun in my opinion. I hope that you will find that fun too. Otherwise, keep listening to your teachers because they know a lot about this stuff. So they can teach you a lot that you might not have that you might not expect. And continue taking, classes when you get to it, you'll be applying to college and high school. And I recommend going to U of I. It's near home, which is always great. But otherwise, in high school, you can also take science. You can also compete in science fairs. So that's if you want to explore, how are these trajectories for the planning, the path that the rocket takes made? How are they calculated? And many other things. But overall, you can also just interact with what NASA does online. They have a lot of, other challenges also for middle schoolers. You don't have to be a college student yet to, do fun things with NASA. Or another thing I recommend is you can go and visit the Kennedy Space Center, do a family trip to Florida. And overall, NASA just has a great set of programs that you should look into. Let your parents know about them. But today's activity, though, is this is going to be our robot. You'll get familiar with what exactly is on, how is it built in a minute. But we'll be programming today's robot in sort of this like block, a block programming language. And actually, how many of you are familiar with Lego Mindstorm from before? Oh, okay, a good amount. Good. Well, make sure to help out your fellow classmates during the activity. Otherwise, we're going to be exploring, some of the challenges that come with like autonomy in programming autonomy into a robot, and also how to use the sensors. How does it that adding sensors improves the performance of your robot? And then some final things that I want to say are a little bit about my experience as an engineering student, specifically in robotics. I have been doing robotics for, I hope that you kind of like take this as like some perspective on like the things that you can work on related to robotics. And it's not just, applications to space. There's so many different things that you can do with robotics, but specifically me, I study what is called control theory and algorithms for autonomy in robots. So that's a lot of fancy words there, but it basically means, how do I write a piece of code that will tell a robot how to solve a problem? So some of the problems that I've worked on are, how many of you have heard of like autonomous vehicles? Yeah, so autonomous vehicles, that's one of the challenges that I was very thankful that I got to work on. And one of the crazy things that I got to do is explore how exactly an autonomous vehicle can be safe. And you might think it's a car. Car, is it a robot? And the answer is yes. In fact, anything that actuates in the physical world can really just be considered a robot. They're called cyber physical systems. And I was focused on developing new methods for the safety control of an autonomous vehicle. And one of the cool projects that I didn't get the chance to work on, but maybe this summer, is, does anyone know what F1 is? Oh, okay, a lot of people know what F1 is. That's good. Well, there's also another challenge that is at the college level. It's more on the graduate school level, but they do autonomous F1 racing, Indy F1 racing, and it's literally an F1 car that drives around at crazy speeds with no driver in it. And it's insane. It just goes around the track and it completes all of it by itself autonomously. So if you're ever interested in that, take a look at it. There are some races in the past couple of years. You should look it up. It's basically just like F1, and that's an interesting challenge. Like, you know, F1 drivers are already so skilled. How do you get a computer system to do the same type of performance? Also, another couple of projects that I think might be interesting are that I'm currently taking a class on robotic manipulation. And we're learning about how robots, like robot arms, learn to pick up and manipulate things, like pick up a cup and place it somewhere, or some cool things that I've seen are like a robot that unloads the dishwasher or puts dishes into the dishwasher. So, you know, if you don't want to do the dishes, maybe you can study robotics, so then you can make a robot that will do the dishes for you. But those are just some of the things that you can do with robotics. There's so much more, and I hope that you'll be able to get a chance to explore that today. So without further ado, I'll take any questions that you all have, anything we've covered. Yeah. Make what type of for our competition, this is the first year that the challenge is different, but in general, we start our development cycle at the beginning of the semester, so in August, and the goal is to finish by March, and that usually ends up being you know, a good 6 months of work, and like 6 to 8 months of work, because there's actually some leeway in between that, but otherwise, each year we build a completely different robot. So the robot that you all saw in the picture, that was that year's design. And the previous years was completely different. And so each year we're always trying to make it better and better and better, and learn from the previous mistakes that we you know, observed in our design. And in case you're wondering, you know, the FLL and like first and facts, like all of those challenges, they also do like a yearly cycle of building the robot. Well, I'm always looking for questions if you all have any, but I think we can get started on